All right, let's unpack this. We're diving into a topic today that usually sends a shiver down the spine of anyone carrying a pager. We are talking about a Kubernetes release, specifically version 1.35.
Released mid-December 2025. And I know the reaction. Usually a new Kube version means scanning change logs for deprecations and wondering, what API is going to break my manifest this time?
Exactly. It's update fatigue. You
Mhm.
see the notification and you just think, great, another weekend gone. But here is where it gets really interesting. We've been poring over the docs and some fantastic analysis by Janakiram MSV from the new stack, and the vibe with 1.35 is, well, it's different.
It is. It doesn't feel like just another feature dump. It feels more like an intervention.
That is the perfect way to frame it.
We often talk about the difference between day one and day two in operations.
Yeah.
Day one is the installation. That's the honeymoon phase. You run the script, the cluster comes up, you high-five your team, and you go to lunch.
And then comes day two.
Then comes day two. That's the marriage. That's the long-term reality of scaling of reliability, security audits, and explaining to your CFO why the cloud bill just doubled. This release, 1.35, is entirely focused on day two. It's about operational maturity.
Which is where we actually live. I mean, we aren't installing clusters every day. We're trying to keep them from falling over. So our mission for this deep dive is to walk through 5 specific features in this release that fundamentally change how you manage a cluster long term. And we have to start with the one that I think justifies the upgrade all by itself. I'm calling it the showstopper.
You must be talking about in-place pod vertical scaling.
Yes, the end of the restart loop of doom. This has been the holy grail for DevOps engineers for years. But before we pop the champagne, can you walk us through why this was such a massive headache historically? What were the mechanics of the old way?
It comes down to immutability. In the container world, we love immutability. But historically, the resource spec of a pod, how much CPU or RAM it requests, that was set in stone the moment you created it.
So if you underestimated your memory by even, 50 megs?
You were stuck. You couldn't just inject more RAM into the container. You had zero recourse. You had to change the deployment spec, which triggers a rollout. Kubernetes would have to kill the existing pod.
Terminate the process completely.
Exactly. And then schedule a new one with the higher limits.
Which sounds fine if you're running a stateless Hello World app. Who cares if that restarts? But for anything stateful.
It's a disaster.
Yeah.
Think about a database shard or a massive Java application that takes 10 minutes just to warm up its cache. When you restart that, you trigger data rebalancing across the cluster, you drop active user connections. It is a heavy, violent operation just for a tiny bit of capacity.
And so, enter Kubernetes 1.35. This feature is now GA, generally available. How does the magic work now? Am I just editing the YAML live while the app is running?
Essentially, yes. You can use standard commands like kubectl patch or kubectl edit to modify the resources, requests field of a running pod. The underlying runtime container, CRIO, whatever you're using, talks to the Linux kernel's two-groups mechanism and just updates the allocation on the fly.
The process doesn't stop. It doesn't even blink. It just looks up and realizes that the ceiling has been lifted.
Correct. It suddenly has more breathing room.
Okay, now I want to be precise here for everyone listening. Does this work for everything? What about, say, storage?
That's the key limitation. This applies strictly to CPU and memory. It does not apply to ephemeral storage. So if you need to expand a local volume, you are still looking at a restart.
But the vast majority of incidents are memory or CPU, right?
Almost always. It's memory pressure or CPU throttling. This solves the big ones.
I immediately think of AI and machine learning workloads here. That feels like the killer use case.
It absolutely is. AI training jobs are incredibly expensive and, time-consuming. Imagine a training run that needs to go for 3 weeks. It's building up this massive state in memory.
Checkpoints, weights, all of it.
Right. And 2 weeks in, you realize the data set's a bit larger than you thought, and you're creeping up on the memory limit.
In the old world, you'd be sweating.
Completely. Because if you hit that limit, the memory killer steps in, terminates the job, and you could lose days of compute time. Now, you just monitor the trend, you see it getting close. You patch the pod to give it another 10 gigs of RAM, and the training just keeps going, uninterrupted.
That saves time, it saves sanity, and it saves a lot of money. But I have to play the skeptic here. This sounds a little dangerous. If I can just magically expand pods whenever I want, what happens when the physical server, the actual node, runs out of space? I can't, download more RAM.
And you've hit on the critical day 2 operational risk. Physics still applies. The Kubernetes scheduler is smart. It tracks the available space on the node. If you try to resize a pod and the node is physically full, the resize simply won't happen.
It just gets rejected.
It enters a status where the resize is pending, or maybe infeasible. But here's the darker scenario operators need to watch. Imagine you resize the request successfully, but you also increase the limits. The node allows it because technically it's just overcommitting.
Which is standard practice. We always promise more than we have, hoping everyone doesn't ask for it at once.
Right. But with in-place scaling, if you resize a pod to be massive and it actually starts using that memory, you create immediate node pressure. Worst case, the node logic kicks in and starts evicting other pods to make room for the big one you just resized.
So you solve the problem for your pod, but you might accidentally murder your neighbor.
Exactly. Requires discipline. You need to be using kubectl describe pod to watch the status of these resize events. And ideally, you're pairing this with the cluster autoscaler.
So if the pods get bigger, the cluster needs to automatically provision more nodes to handle the load.
Precisely. You can't view this feature in isolation. It has to be part of your bigger capacity planning strategy.
Makes sense. It's a superpower, but you need to control it. Okay, let's move to the second feature, which addresses a different kind of neighbor problem: security. This one is called fine-grained supplemental group control.
It's a mouthful of a name, but for anyone running a multi-tenant cluster, this is huge.
Set the scene for us. What was the security hole we were living with before 1.35?
It was an issue of inheritance. In Kubernetes, you have the pod security context. This is where you define things like which user ID runs the app, and crucially, which Unix groups the app belongs to.
Standard Linux stuff. Group A can read the database file. Group B can write to the log directory.
Right. The problem was these supplemental groups were defined at the pod level, and a pod, as we know, can have multiple containers.
I see where this is going. So if I have my main application container and then a tiny sidecar, say, a logging agent.
They both inherited the exact same keys to the castle. The sidecar got every single group ID that the main application had. It was an all-or-nothing model.
Which completely violates the principle of least privilege.
Totally. If an attacker compromised your metric sidecar, which might be running third-party code you haven't fully vetted, they suddenly had the file permissions of your main database application.
So 1.35 introduces granular control. How specific can we get now?
It's now GA, and it lets you define supplemental groups at the container level.
So I can explicitly say, main app gets the database keys, sidecar gets nothing.
Exactly. And they introduced a policy field to control this. You have a merge mode, which acts like the old way, it just blends them. But the game changer is strict mode.
Strict means what I say is what you get, no inheritance.
Yes. It completely ignores the pod level settings for that container. This is massive for compliance.
I imagine anyone working in fintech or healthcare is nodding their head right now.
Oh, absolutely. If you're auditing against PCI or HIPAA or the CIS benchmarks, you have to prove isolation. You have to prove the logging agent cannot read the patient data file. Before this, that was technically very hard to enforce inside a pod. Now it's just a line of YAML.
It also sounds like it helps with legacy apps, right? The ones that need weird permissions.
It does. You can isolate those quirks to just one container without exposing the rest of the pod.
It really feels like Kubernetes is finally giving us the tools to clean up the messes we've been making. Speaking of which, let's talk network traffic. Feature number 3 prefers a node traffic distribution.
This is one of those features that sounds boring and technical until you look at your cloud bill.
Okay, so break down the inefficiency. We have a cluster, lots of services talking to each other. What's happening in a standard setup that wastes money?
We call it hairpinning. Imagine service A needs to call service B. In a dense cluster, it's very likely that an instance of service A and an instance of service B are running on the exact same physical server.
Your neighbors on the same motherboard.
Right. But the default Kubernetes networking logic, it's all about randomness and availability. It spreads traffic across all available endpoints. So service A might send a packet that leaves the node, goes out to the network switch, travels across the data center, and lands on a different node just to hit service B.
Even though service B was sitting right there.
Correct. You're incurring latency, using up bandwidth, and in the public cloud AWS, Google Azure, you're often paying for that data transfer, especially across availability zones.
The interzone data transfer line item that makes CFOs cry.
That's the one. So 1.35 introduces this traffic distribution field with the setting prefer some node. It just tells the internal load balancer, look locally first. If the service you're trying to reach has an endpoint on this machine, use it. Don't go out to the network unless you absolutely have to.
This seems like a no-brainer for sidecars or service meshes like Istio.
It's huge for them. And for caching layers too, like Redis. If you deploy a Redis replica on every node, you want your app to talk to the local one, not one across the cluster.
Is there a downside? I mean, if we stop randomizing traffic, don't we risk creating hotspots?
You hit the nail on the head. That is the trade-off. If you have one node that's super busy and you force all traffic to stay local on that node, you're just hammering that CPU while other nodes might be idle.
So locality comes at the cost of balance.
It can. That's why the feature is called Prefer Some Node, not Force Some Node. But you still need to be careful. You should monitor this. Keep an eye on your CPU load averages. You might need to tune your horizontal pod autoscaler to react faster if a single node gets overwhelmed.
So great for cost and speed, but requires monitoring. Okay, feature number 4. This one is less about the runtime and more about the setup headache. Structured authentication configuration.
Or, as I like to call it, the death of the flag soup.
The flag soup, I love that. Explain the misery of the old way.
The Kube app server, the brain of the cluster, is configured with command line flags. For years, if you wanted to set up OIDC like logging in with Google, you had to pass these massive, complicated strings of text as flags.
And if you made one typo?
The API server fails to start. Or worse, it starts, but your security config is wrong. And because they're startup flags, they are so hard to manage. It's brittle.
And it's definitely not GitOps.
Exactly. You couldn't really version control your auth logic easily because it was just buried in some system config file.
So 1.35 brings structured authentication configuration. I assume this means we finally get a nice clean config file.
Yes, a proper version structured YAML file. You define your OIDC providers, your rules, all in one place. And you just point the API server to that one file.
And why is that such a big deal for the day 2 operator?
It's all about the workflow. It fits into your CD pipeline. You can now put your auth-config.yaml in a Git repository.
Right, so if I want to add a new OIDC provider, I don't SSH into the master. I open a pull request.
Exactly. You open a PR, your security team reviews it, you merge it. A tool like Argo CD or Flex applies it. You have a perfect audit trail of who changed the login rules and when.
That is a massive security upgrade. It moves authentication from some arcane setting to visible versioned code.
It just lowers the barrier to entry for having a secure cluster. And looking forward, this architecture paves the way for hot reloads changing auth rules without even restarting the API server.
Operational sanity. I love it. Okay, let's talk about the final feature. This one is a bit tricky. OCI image volumes.
This is my personal favorite for pure innovation. It really changes how we think about data.
We all know OCI images. They're Docker containers. We run them. But you're telling me 1.35 lets us use them as hard drives.
Effectively, yes. Think about what an OCI image actually is. It's just a tarball of files with a manifest stored in a registry.
Sure.
Usually Kubernetes downloads that, unpacks it, and executes a binary inside. But what if you don't want to execute it? What if you just want the files?
Give me an example. Why would I want just the files?
The biggest use case right now is large language models and AI.
AI again. It's driving everything.
Always. An AI model is just a giant file or set of files that could be 10, 20 gigabytes. Traditionally, you bake this model into your application container image.
Which makes the app image massive.
Massive. Slow to build, slow to push, slow to pull. And if you change one line of code in your app, you have to rebuild and push that whole 20 gigabyte layer. It's incredibly inefficient.
So with OCI image volumes, you separate them.
Exactly. You package the model as its own OCI artifact, just the data, you push it to your registry. Then, in your pod spec, you mount that image as a read-only volume.
So it just looks like a USB drive plugged into the container.
So that's a perfect analogy. A read-only USB drive. The application container starts up, looks at, say, MNT model, and all the files are there. The application container stays tiny.
That is brilliant. So I can update my code completely independently of my model.
And you can version control your data using the same tools you use for code. Container signing, vulnerability scanning, all that infrastructure now applies to your data artifacts.
And it's read-only, which is a nice security feature.
It is. The container cannot corrupt the model or inject malicious code into that volume. It's immutable at runtime.
This also feels great for CI/CD pipelines, like for shared tools.
Yes. If you have a set of scripts or binaries that every step needs, don't copy them into every container. Just mount the utilities image as a volume.
So looking at these 5 features in place, resizing, fine-grained security, local traffic routing, structured auth, and image volumes, there's a really clear theme here.
Resilience and efficiency.
It feels like Kubernetes is growing up. It's no longer just about how do we orchestrate containers. It's how do we do this cheaper, safer, and with less downtime.
It's shifting the burden from the human operator to the platform. The platform now handles the resizing. The platform handles the traffic optimization.
But, and there is always a but, I want to leave the listener with a thought experiment. We talked about in-place pod resizing being the showstopper.
The end of the restart.
Right. If we truly reach a point where pods never die, where we can patch them, resize them, update them, all without a restart, does that change how we design systems?
That's a deep question.
Because the whole philosophy of cloud native was built on the idea that infrastructure is ephemeral, cattle, not pets. We built resilient systems because we expected pods to die constantly.
You're asking if we risk becoming complacent.
Exactly. If the pod becomes immortal, do we stop building chaos monkeys? Do we stop handling graceful shutdowns in our code because, oh, the pod will just resize, it won't crash?
It's the self-driving car paradox. If the car is too safe, the driver stops paying attention. I think the danger is real. We have to remember that hardware still fails. The node will die eventually. If you optimize your app to never restart, you might be in for a very rude awakening when the physical power supply blows.
A very valid warning. Just because you can keep a pod alive forever doesn't mean you shouldn't be ready for it to vanish instantly.
Always designed for failure. That hasn't changed.
All right, here is the mission for everyone listening. Don't just take our word for it. You need to get your hands dirty.
But not in production, please.
Yes, keep your resume safe. Spin up a test cluster with 1.35. I specifically want you to try the prefer some node traffic setting. If you are running a high traffic environment, turn that on, run some benchmarks, and see if it actually drops your latency and saves you money.
And try the structured auth. Even if you don't need it today, getting your configs into Git now is going to save you so much pain later on.
Kubernetes 1.35. It's not the flashy release, it's the smart release. Thanks for diving in with us.
Pleasure as always.
See you on the next deep dive.